Welcome to this lecture of Vehicle Dynamics and Electric Motor Drives. We have seen the modeling of permanent magnet synchronous machine in the last lecture, and in this lecture we are going to continue with the design of the vector control, design of the control for the PMSM drive. So the vector control of PMSM drive has few segments. First one is the design of the controllers, and second is the implementation of the same. Since we have done the modeling, we are already familiar with the block diagram for the complete control structure. We would like to redraw and we will continue with the same. So let us recap the block diagram of the PMSM drive, what we have drawn in the previous lecture. So we are trying to have speed control of the PMSM drive. For that, a speed reference is provided to the system, and that is denoted by omega star. And in the feedback based control, we are having the feedback of the speed available with us. So that is compared, that is subtracted from the reference, and the error is fed to the PI controller, as we have seen in the previous class. The PI controller for the speed is basically generating the reference for Q axis current, and this reference is once again compared with the feedback ISQ current. Once again, the error is fed to the PI controller, which is responsible for maintaining the reference current, and the output is basically corrected by considering the feed forward terms. The resultant signal is basically fed to the inverter. This can be called as VSQ star, and inverter is modeled as a gain with value VDC by 2. The output generated by inverter in the DQ frame of reference, VSQ, is basically fed to the machine, where the model has two nonlinear components which are getting subtracted from the voltage and there is an RL block corresponding to the resistance and inductance of the stator winding, and we are finally receiving the ISQ current. Now this ISQ current is responsible for generating the torque, electromagnetic torque in the machine, which is fed to the mechanical model after subtracting the load torque. And mechanical model, we have considered the worst case scenario when there is no friction involved in the system, and the speed, mechanical speed, is generated after this. Now what we have done is that we are taking feedback of the current and feedback of the mechanical speed. However, the speed feedback involves a low pass filter. We have first order filter where the structure can be taken as 1 divided by 1 plus tau f. So this is the control structure what we have seen in the previous class. Now the nonlinear terms, as I said, are basically compensated through the feed forward terms. So the effect of nonlinear component is compensated in advance, which is why while designing the controller, we can ignore them as a disturbance in the system. Now, going for the other part of the model, which is d-axis model, since we are trying to maintain our d-axis current equal to 0, which means we are neither drawing any reactive power from the supply nor feeding any reactive power to the supply, we are maintaining ISD equal to 0, which is why the reference is considered at this value, and this is compared with the feedback ISD current. Error is fed to the PI controller, and then we have the output of the current controller generated over here, which is once again corrected through the feed forward term, which corresponds to the cross coupling. Now the resultant reference signal VSD star is basically fed to the inverter model, which is given by VDC by 2, and VSD voltage is generated from the inverter, where we have the nonlinear component of the model and the linear part of the model, which is RL component, ultimately producing the current ISD, which is taken as feedback for the control action. Now, when we see the current d-axis current control, this is pretty simplified structure. We have only one control loop available over here. However, if we see the speed control loop, we are finding that the ISQ control loop is basically sitting inside the speed control loop. So I can mark that within this red box. Now once again, going by the method what we have considered for DC motor control, whenever we have multiple control loops coming within each other, we need to consider cascaded control approach. We need to have a mechanism to design the controllers independent of each other, and in some way we should be able to decouple the impact of one controller on the other. So these two control blocks, which is one within this red block and the other outside the red block, are basically decoupled, and these are designed independently. So how this decoupling can be made possible? First, what is the meaning of decoupling that we need to understand? When we are suggesting that current and speed control loops are independent, what essentially it means that the dynamics is quite different for the two control loops. So in a way, what we are trying to suggest is that our inner current control loop is much faster compared to the outer speed control loop, and the impact of that is speed control loop observes nearly unity gain block in place of the current control loop. So what is suggested over here is that when we are trying to match the reference current and the output current, we are trying to say that if a reference is provided at this moment, with respect to the outer control loop, our actual current is able to track it within no time. So before any action starts happening in the speed control loop, we have our current control loop settled and the ISQ is already tracking the ISQ reference. So in effect, what we are going to have is approximately a unity gain block is going to be realized in place of the inner current control loop. However, yes, because the control cannot be instantaneous, so we will have some delay, and instead of unity gain block, we will have a first order gain block available over here. So taking it further, we can conclude that the bandwidth of speed control loop is much smaller compared to bandwidth of current control loop. So if we denote omega b omega as the bandwidth of the speed control loop, we are saying that this is much smaller compared to bandwidth of current control loop denoted by omega b omega I. In fact, we need to have clear understanding of what is the definition of very, very less. So here we can take a rule of thumb is that this is going to be nearly 1/10 of the bandwidth of the current control loop. So using this, what we can say that even before the speed control loop starts any action, our current control loop is already settled. Now let us go ahead and realize this control structure. So we can take out the current control loop from the combined control structure and we can place it separately. The PI controller can be written as Kp plus Ki by S, and we can mark a superscript I to differentiate it from the speed controller Pi. Now, as I have said, the disturbances are ignored for the controller design, for the design of Kp and Ki values. So which is why the output generated by the PI controller is now fed to the gain VDC by 2, which is the inverter model, and output of that is basically fed to the first order plant. And we have the feedback of ISQ appearing over here. Now, to design the parameters Kp and Ki, we need to have certain rules. We need to set certain rules, and then we need to formulate Kp Ki in terms of the motor parameters and the restrictions what we are going to impose. So if we write the open loop gain of this system, the current control loop, we are going to have this. Now we can segregate these terms for the purpose of simplification. So what we find that we have structure where there is a pole at origin, a zero at the location as per the design of the controller, and another pole coming with a time constant of Ls by Rs. Now, if we think of it, think of the circuit, what we are having apart from the nonlinear components, we have RL circuit available over there and we are feeding some voltage to it. Now, this circuit as such cannot go unstable because of the availability of only one pole. There is no resonance possibility over here. However, we would like to have a quick response from this circuit. So which is why we would like to compensate for the slower pole which is available on account of the parameters, and for doing that we will use the zero found by the controller, PI controller over there. So what we are trying to state is that we will have pole zero cancellation for compensation of the slower pole. What it effectively means is that we are trying to have the ratio of KPKI going equal to L by R. So now this gives us first equation for the design of our current controller parameters. Now once we have said that we are making this rule, which means that the impact of zero and impact of pole are basically cancelling each other. Now the remaining components can be taken out further and we can segregate it in this manner. For the complete design, we need basically one more equation. So, which is where we are going to set a rule on the bandwidth of the current controller. Now, we have said that our speed control bandwidth must be 1/10 of the current control loop bandwidth. However, we have not said any absolute value for the current control loop bandwidth. So, now here we can define what is the current control loop bandwidth by having the closed loop transfer function of the current control loop after the cancellation of the pole zero, and we are going to finally reach up to so the bandwidth of current control loop is now formulated as Ki VDC by 2 divided by Rs. Now we can fix the bandwidth of the current control loop as per our requirement, which means we would want the system to be as fast as possible. However, there is limitation on account of PWM and inverter action. So we must note that the voltage generated by inverter is happening through one of the example what we have seen in case of sine triangle PWM is happening through the modulating signal and carrier comparison. So there is a limit that how fast the output can be realized from this kind of system, and this is where another rule of thumb can be established is that we can achieve the highest bandwidth for the current controller as 1/10 of the switching frequency. In case of two-level inverter, this is also carrier frequency. So what we are trying to state over here is that if we are having a switching frequency of 1 kilohertz, we can comfortably achieve bandwidth frequency of 100 hertz for the current control loop. So for the purpose of omega, 2 pi is included in this equation. Hence, the bandwidth can now be equated to 2 pi by 10, 2 pi fsw by 10. And Ki value can be represented in terms of switching frequency, resistance, and the gain of the inverter. Similarly, we can write the formula for Kp as well. So now, if we see over here, the control loop for the Q axis current and the D axis current are identical. Apart from the cross coupling terms and nonlinear terms, the plant is same, gain is same, and which is why we can have the same controller design for both the control loops. So we can have the same value of Kp and Ki for the Pi controller involved with the D axis controller. So this completes the design of the current control loop controller, and now we can proceed with what is suggested as the speed control loop. Now, as observed, our closed loop structure for the current controller is looking like a first order system, what is stated earlier. Say this bandwidth what we are maintaining and corresponding time constant can be defined as tau I, which is 1 by omega b omega I. So tau I can be written as or tau A can simply be written as 10 divided by 2 pi fsw, which is the inverse of omega b omega I. So this current control loop in the complete structure can now be simplified, and it can be written as so we'll take up the design for the speed controller for this control loop from here. And for clarity, speed controller Pi will be represented by Kp omega plus Ki omega by S. So what we have the reference for the speed, feedback for the speed, filtered feedback for speed. This is being fed to the PI controller, and the output is basically the reference ISQ current, which is effectively passing through this first order block to generate the actual current ISQ, and this ISQ current is basically responsible for generating the torque, where after ignoring the disturbance tau L, we have the mechanical model and our mechanical speed is generated. In the feedback path, we have considered a first order filter which can be represented by 1 by 1 plus S tau F. Now, if we write the open loop gain for this control block, control loop, it has the controller, plant of the closed current control loop, and the mechanical model for the machine, and also the filter which is going to be present in the feedback path. Now, once again, this can be simplified and it can be structured in a better manner. So we have so altogether there are several poles located at different locations in this system. However, the dominant poles for this system are located at origin. And because there is presence of multiple poles in the system is inherently unstable, and which is why we can have a way to simplify the structure for the rest of the pole arrangements. So what can be done, because compared to origin, these two poles are coming at a little bit far distance, little bit far frequency, so it can be combined to have a cumulative, a kind of some fictitious pole which is basically giving the impact corresponding to both the poles which are there. So in other words, basically what is attempted over here is that if we take product of these two terms, we are going to have a second order system. Now the coefficients of the second order system involve sum of the time constant for these two pole locations and the product of the time constant for these two pole locations. Now, if we go by the relative magnitude of these time constants, what we observe that typically we would like to have a bandwidth of say 100 hertz or 500 hertz, something like that, for the current control loop, so which is going to be of the order of millisecond. The time constant is going to be of the order of 1 or 2 millisecond, whereas filter is something which is placed at a much lower frequency. So many a times it is placed somewhere around 10 hertz or 5 hertz kind of location, so which is effectively 1 by 2 pi times of 10. Nearly we can say something like 0.06 second or nearly 16 millisecond. Now in comparison to 16 millisecond, a millisecond is a small number. So some if we call that as a new value tau 1, is going to be nearly equal to tau f, or for better accuracy we can consider the exact value of tau I and tau f. However, the product for the two time constants is going to be of the order of 10 to the power minus 6, which can be conveniently ignored in comparison to the magnitude of the other coefficients. So which is why the product can be approximated to a new first order system which is equivalent to representing these two pole locations, where tau 1 is given as the sum of the two time constants. So after considering this simplification, our open loop transfer function is going to look like so. In this scenario, what we basically have is that there are couple of poles located at the origin and a zero located according to the design of the controller, and a pole which is coming at a little farther frequency, so nearly about the filter frequency what we have. Now if we try to draw the Bode plot of this system to understand the stability, what we find is that because of the presence of a second order pole at origin, the magnitude plot is going to have a slope of minus 40 dB per decade, and it is going to continue up to the gain crossover frequency if there are no other poles or zeros located in the vicinity. Now if we look at the phase plot of the system, once again because of second order pole at origin, the phase is going to be at minus 180 degree, and it is going to continue at that if there are no other poles or zero located in the vicinity. So what is observed is that because at the gain crossover frequency we have phase coming as at minus 180, which means that we have a scenario of phase margin going to 0 degree, which indicates that the system is unstable, and therefore we need to take some corrective action for the phase margin so that the system can be made stable. Now this is not possible through the pole zero cancellation of this part, because these are frequencies which are located much far from the gain crossover frequency until and unless we make some corrective action over there. So which is why we go for a method for solving this scenario, and that is called symmetric optimum method. For the DC motor control also we have seen a similar scenario, and we have tried to solve through the same technique. So here what we are going to do is that we are going to place this 0 and this pole symmetrically about the gain crossover frequency for the open loop, which is also the bandwidth frequency for the closed loop system. So let us assume that the ratio of the two frequencies is A, which means that bandwidth of speed and 0 are having a ratio A, and the pole and the bandwidth are also having the same ratio. So because we are talking about logarithmic x-axis, which is why the distance between the frequencies is going to look same in this scenario. So effectively what we are going to observe is that as we place the zero, say suppose somewhere here, and the moment this corner frequency is encountered, the slope of this magnitude plot is going to change and it is going to become minus 20 dB per decade. And it is going to continue. Now because our next pole is going to come after certain after the gain crossover frequency, the new gain crossover frequency, so this plot is going to cross the gain crossover frequency with a slope of minus 20 dB per decade. And then the moment it encounters the pole location, it will return back to the slope of minus 40 dB per decade. Now the impact of this change is going to be seen on the phase plot of the system. Because of the change in slope, the phase will start improving, and somewhere at the gain crossover frequency or at the bandwidth frequency, it will maximize and it will return back to minus 180 degree. Now at the gain crossover frequency, we are going to have certain phase margin available for the stability of the system. So which is why now we can say that with the location of new zero and pole, our system is going to be stable. Now because we have introduced one more variable in the system, now we have three variables to be solved. We have Kp omega, Ki omega and A. So of course we have got our first equation over here. Now we need two more equations for solving this complete set. So again, the equation can be derived from this scenario. Now what we are trying to impose is that we want a phase of minus 180 degree plus phase margin for the open loop system at a frequency of omega b omega, which is the gain crossover frequency. This is the second scenario. And the third one is that we want this gain plot to cross the 0 dB line at omega b omega. So that's another condition what we need to impose on that. So gain of the open loop system at omega b omega is going to be 1. So these three conditions we are going to use, and we are going to solve these three variables. Now going by the second equation what we have, we need to write the phase of the open loop system. So the constant term is not going to contribute anything on the phase side, and the double pole is going to have a phase of minus 180 degree, whereas the 0 will have a phase of plus tan inverse of omega by omega z, whereas the 0 will have minus, whereas the pole will have minus tan inverse of omega by omega p. So altogether what we are going to observe now, using the first condition, we can plug in this over here to simplify this as tan inverse of A minus tan inverse of 1 by A going to phase margin. Now what could be a suitable phase margin for the system? So we can say that a phase margin of 45 degree would be good enough to make the system stable. Now considering this, it can be solved and it will result into a quadratic equation which can be given by this. Now this quadratic equation will have two solutions, and that can be written as 1 plus minus root 2. Now because we are looking for ratio between frequency, so A must be a positive number, and hence value for A is chosen as 1 plus root 2. Now going ahead, we can take the gain of the system and we can equate it to 1. So this equation can be simplified once again by using equation 1, and we can obtain the value of Ki in terms of system parameters and A. So this exercise is given to students and the candidates for solving it and getting the exact value. It's a simple exercise to be done, and we can move further with the implementation part for the controller. Now, as we have done the design for the current controller, we also need to understand that we have a physical system which we are trying to realize through these controllers, which means that the output generated by the controller must have certain limitations. For example, when we are generating the reference signal VSQ, we cannot have any value for VSQ because eventually VSQ is going to reflect on the modulating signal. So we need to have saturation limits for the controller, and also we need to have anti-wind up possibility for the integrator which is available in the system. So as we have previously discussed, if we have provided an error of a constant value, the integrator will have tendency to assume a very high value, and if meanwhile our error is changing its nature, the integrator is going to take a lot of time to return back to any value which will be useful for the negative error. So to avoid this phenomena, we generally need to stop the integration process after certain value. So what is done essentially is that as this integrator is moving further and reaching a value which is near close to the maximum value possible for the control signal, we need to stop the process of integration, and that is what can be called as the anti-wind up technique for this integrator. So we are going to have, when we are realizing our PI controller, we have the error which is getting fed to proportional, which is a gain, and the integrator part which is gain, as well as an integration block. We need to place a saturation limit or stop limit for the integrator within the block itself, and then these two signals can be added to provide the final output. However, to limit VSQ within allowable value, we need to have saturation for the complete component. So we need to have a saturation block over here. Now we can work out the value of this saturation limit VSQ on basis of the maximum modulating signal value or maximum modulation index. So as we understand that our individual component VSD VSQ, which is basically part of the voltage vector, these are the components of the voltage vector, are going to have a magnitude which is 1.5 times of the peak value of the individual phase quantity, which is why VSQ can be allowed to And in case of linear modulation, we are keeping the saturation limit to 1. So which is why we say that the saturation value for VSQ can be considered as 1.5 on either side. So we have saturation limit given from 1.5 to minus 1.5. Now, when we talk about the speed controller, which is essentially generating the ISQ reference, once again, this ISQ reference should be limited to the system current rating. So if we are dealing with a system where per phase RMS value is say IRMS, which means that the ISQ value of current may reach up to root 2 times of RMS multiplied by 1.5. So this can give us an understanding about how much saturation limit should be kept on ISQ reference. For a short time, we may provide a cushion of say 20% extra current for quick acceleration. However, this extra current limit is only for short duration. We are not supposed to operate with increased value of current for a very long time because of thermal constraints. So thus we have completed the design as well as saturation limit for the controllers. Now we can look for the implementation part for the system, for the vector control of PMSM. So as I have indicated in the previous lecture, there are two parts in the system. We have hardware and then we have software. Software essentially involves the controller which is designed as per the requirements. So we have already done that. However, when we are implementing, the block diagram is essentially only for the purpose of the design of the controller. Ultimately, the software is going to give command to the hardware in terms of only modulating signals or getting signals. So if I draw the physical structure, we have an inverter, which is feeding to motor. Motor is connected to load. Where tau L, tau E, omega M are the usual quantities what we have considered. Now, in the control section where we are providing the reference, so we have the omega reference provided over here. Omega feedback is generated at this point of time. We have the PI controller which is essentially generating ISQ reference. we have the feedback for ISQ given to the current PI controller, which is essentially generating the signal which is corrected for the feed forward terms, and eventually we generate the reference for the Q axis voltage. Similarly, we have the D axis current reference set at a fixed value, in this case 0, fed to the PI controller, and then that signal is corrected corresponding to the feed forward term, and a signal VSD is generated. Now, because we have PWM techniques which are essentially involving sinusoidal modulating signals, this VSD and VSQ has to be transformed to sinusoidal quantities which are actually our modulating signals, and this transformation essentially needs the unit vectors sin rho and cos rho. Now, this modulating signal can be compared with triangular carrier, or it can be used for any other PWM block for generation of the gating pulses. Essentially, these gating signals are fed to the gate driver unit of the converter. Now, when we are going for the feedback, we do need ISD ISQ current, which means that we need to measure three-phase sinusoidal current over here, and this measured current is required to be transformed to DQ, which is eventually fed to the system, to the controller. Now, taken from the speed encoder, and we have omega m available, which after a filter is fed to the PI controller block. So, this is how we can realize the vector control, whether on simulation or on hardware. Now, for these conversions, we are basically requiring sin rho and cos rho unit vectors, which can essentially be derived from the speed encoder or resolver mounted on the PM machine. So this can provide us the sin rho and cos rho. So it concludes the vector control of the PMSM drive, where we have seen how we can model the machine in a convenient manner where the linear controllers can be applied. Then we have done the design of the controllers, and we have seen the saturation limits and implementation of the same on any simulation platform or any hardware which can be taken up further. So that is all for this lecture, and then we will go ahead with the induction motor modeling and control in the next lectures. Thank you.